but we are section 6.4 trying to figure out our 4 evens. Section 6.4 trying to figure out 4 evens. Evens gone. And then, so you guys, I mean, you really shouldn't need to take long on these because number 2 is literally just the dot product formula. It's written the academic way. It's written the official horizontal times horizontal of 2 vectors plus vertical times vertical. Number 4 is just the term orthogonal that we talked about on Friday. Number 12, linear combinations, then plugged into the vector dot product formula. But I don't know. How many of you guys, look at your work on number 12 real quick. I'm just curious. How many of you guys wrote them with components first? Just 2? Really? I mean, I get it. My brain could have gone straight to the formula too. You guys know what I mean by components. Nathan, when I said components, how did you recognize it on your paper? What are components again? Yeah, the sideways carrots, technically. But yeah, the sideways carrots. Did anybody else write those sideways carrots for number 12? Oh, there we go. 1, 2, 3. Huh. Okay. I mean, you didn't have to. Just could have helped your brain process it. And then number 82 was one of those work problems. Now remember, there are some complicated ideas. The people who were here on Thursday when a lot of you guys were gone, there were complicated ideas in section, what is this, 6.4? With projection, but remember, I told you, the work problems aren't going to be that hard. So if you didn't get number 82, you're missing, I can quote Mililani, you're missing the point, just not in a much bigger, more important sense that she was sharing, just mathematically speaking in this section. Not near as important. But you're missing the point if you didn't get number 82, because I was like, oh, they're going to be easy. And this one was easy. Look how short it is. But real quick, can I just show you the work? You had something being dragged. And as it was being dragged, it was actually being pulled at an angle. Oh, it's going to totally mess it up, isn't it? And that angle was 30 degrees. So it's being pulled at an angle, but it's dragging across the ground, and it's dragging a certain distance, and then there's your, I don't know. Do you guys have what it was? Was it a log? Was it a...
It was an Olympic box weightlifter dragging a cement block.
Oh, got it. So not like a weightlifter, like those guys who like pull semis with their teeth. Anyway, coming back. Which makes me hurt thinking about it. I know it just messed up the whole formatting, but here's still my picture of someone's dragging, putting their back into it once again, that cement block. So even though he's dragging it this way, and that is the force, and they say that force is, I'm guessing, 250? Did I put that in the right spot? It's 250 the newtons, how hard he's pulling? And 100 is the distance. Oh, they didn't say newtons, sorry, they put pounds. There we go. So he's pulling at a force of 250 pounds over his shoulder. No, it is newtons. He's pulling it, oh, so he's doing this way. But still the cement block, and then it's at an angle. Okay, thanks. We'll say that's it. So he has that 250 pounds that he's pulling at an angle. The angle is 30 degrees, 100 feet. Remember, all we need for our formula is force times distance. But here's the struggle. They gave us a force, it just isn't the right one. What's the one that I need for my formula? This one. That was slow. That one. So how do I solve? Just kidding, SOHCAHTOA is enough. I want my x to be able to plug in, to be able to multiply by my 100 feet. And so if you guys didn't realize, it was easy as solving a right triangle adjacent over hypotenuse is cosine. And once you have cosine of, how's it going? Chapel? Yeah, that's what you do. If nothing else, in the sense of, I'm speaking, understanding that your perspective and my perspective are very different when it comes to chapel, right? Like students' perspective and teachers. And even among students, very different perspectives as to how much it's appreciated, etc. So I'm saying if nothing else from your vantage point. If nothing else, it, definitely trying to change up chapels this year, right? And make them more practical. And even if you're like, I think that's stuff to appreciate. Just kind of thinking, like trying to start conversation and dialogue and getting real and getting helpful, or at least practical, at least current. Just, I don't know. If you're not having like an appreciative, you're changing it up this year. Even if like you're not totally appreciating it, just think about it. Like I think it's a really useful, really healthy thing that they're trying to do. And Mililani's, she's a huge blessing to me, and I hope she was to you today as well. P.S. She keeps up a blog. When one of her classmates came to see us last year, she just dropped by chapel. She wasn't speaking. She was just in the back, and she was just praying for you guys and just kind of wanting to come home, if that makes sense. She had met with a lot of her kids that she had graduated with for the year that graduated 2 years ago. It was a really hard time, and yet they really found support in each other. The anniversary of Colby's death was January 24th, so just a couple weeks ago. But just know that she loves you guys a lot, and she knows that the experience here as a student is not perfect. She knows it very well. And she knows that once you graduate from here, life can be really hard. So, anyway, she loves you guys a lot. And it was cool just how honest she was with you. But I think she also has a blog, because she started writing in that blog. She was like, hey, check out my blog. I wrote about Colton. And anyway, all things to think about, especially if you go to Shepherd, whether or not you're part of the youth group. She's a good one to talk to about things if you ever needed to. Solving our right triangle. I think maybe my computer's alive again. It has cosine 30 written there. That's good. We have our adjacent being x over hypotenuse, which is the y. So all they did is just solve for x, 250 cosine 30, and then multiply it by 100. So the really cool thing in thinking towards the test that is this Thursday, if you got overwhelmed by section 6.4 at all, do you guys realize the example in our notes was the exact same thing? It was the diagonal force being exerted, cosine of the angle times the distance. Like, do you think you could, like, when it comes to making a formula card, which I've already said you're allowed to have for section 6.3, 6.4, 6.5, diagrams, formulas, terms, I don't know what else you want to put on there. Pictures of things on hills with little triangles. Anything and everything besides actual examples with numbers filled in. Because as soon as you put an example with a number filled in, if I change something on the test, it could throw you off. So I only want you to put general things. But if you guys realize, technically, what you could do to make your life easier is exactly what I showed right here. You already know what kind of work problem I'm going to put on the test, because I already talked about it. And I already talked about it's not going to be at a weird angle where you need to figure out dot products with projections. I said it's going to be something on a horizontal surface that's being dragged at an angle or pulled at an angle or whatever. Force exerted at an angle. You could literally just say, hey, what is that diagonal force? Cosine of the angle to which it's with times distance. Like, you guys don't have to use either one of these kind of weird out there for harder problems formulas. You can literally use what we've seen in notes and then now again in homework. I'm trying to help you on your study strategies, because just a few of you haven't quite gotten there yet as far as how to study for these tests. And maybe the formula card thing is a godsend in some ways, especially for vectors, which is 6.3 and 6.4. But if you just put down formulas that you don't understand, you're not going to get the things right because you won't know how to use them. Tools are only as good as your ability to be able to use them well and properly, right? Send me into the woodshop and I'll be like, what I'm going to make is not going to, it's going to pale in comparison to what Mr. Horn can make with his tools, right? I'm just going to mess things up and probably chop off fingers. So, hopefully not. Hopefully I'm a little bit more careful with that. I'll probably drop something on my phone, knowing me, I've broken the toe and broken the foot. But anyway, coming back, I'm clumsy. What I can do with his tools pales in comparison to what he can do with his tools. Why? Because he knows how to use them, and he's gotten a lot of practice in. So, just Please, these are tools, but a formula card isn't going to make your life so much amazing, like so amazing that you're going to get an A on the test. You have to be able to put down tools that you know how to use. Okay. I know. Just some of you, I'm like, you could be doing so much better. I know you're good students, and you just have to figure out how to study for this class. And pre-calculus is pre-everything future math, and not math classes. Math tools, and math tools are used in all sorts of different places. Okay. Love you, care about you. That's the only reason I keep talking. But right now, I'm going to care for you and stop talking and see if you have questions. What do you guys need to see? Is there anything else you can? Yeah, Griffin.
19.
Perfect. We're going to check out 19. Anything else you need to check out?
71.
71. Let's go do 19. Let's go do 71. You know me. I'll do a last check, okay? So number 19. Nice thing is number 19 isn't super complicated as far as words and scenarios and some weightlifter Olympic pulling. I don't even know. But it is a little bit complicated in terms of there's a lot going on. So number 19, if you guys check it. 19, right, Griffin?
Yeah.
Okay. 71. I saw it backwards. We have a dot product. And then we have a multiplication that doesn't have a dot, but I wonder if it's supposed to be a dot. We'll figure out in context. PEMDAS, parentheses first. It works for vectors. So we want to do a dot product, but technically we don't just want W, we want a 3W. So coming back up here, and you guys, can you just check real fast in your homework? Are you guys throwing the vector arrow where you're supposed to be throwing? Okay. So we're tripling W, which is going to be 9, -3, dot product with V, which is going to be -4, 2. My brain, I just like seeing the components and then doing the dot product. To be honest, if I was doing the homework, I would probably do it all mental math. I'll be honest. But for showing the work and trying to make sure you guys understand, I'm showing out the steps the way my brain kind of thinks through it. So I would triple the W, dot product with the V. I still have this whole U thing, so technically, that's out here. I'm just going to write it because we'll get to U in a second. As in that U. I'm getting to you right now. Stop. Dot product. First, but second, right? So we have -36 multiplying 9 plus 9 times -4. Dot product adds vertical, which will be -6. So that's what's inside my parentheses with that U on the outside. So then, Griffin, what I'm seeing is a -42, which is just a number. Dot products always result in what we call in physics scalars. Dimensionless, just a single constant. So I'm going to distribute. So here's my U right up here. So if you can visualize it, you're just distributing this to each and every component. If it helps, you could write it out and actually be like, oh, hey, I know who U is. U is 3. So my final answer would just be -42 times 3, which, double check my math, -126. Dun. Just slow and steady wins the race. PEMDAS, start on the inside. Triple that W, dot product with that V, and then multiply. Which in some ways is kind of cool in the sense of maybe for the first time this year, you guys are like, man, if I had walked in beginning of chapter 6 or before we started chapter 6, you wouldn't have known like half the words I just said. Okay. Don't get lost. Number 71. Spencer, I'm guessing is kind of more of a word problem, yeah? Oh, and that's why my book hates it. Go team. I don't think it's my computer. I think it's the file. This book is a mammoth PDF, which is why I can't even post it online for you guys to see. Just a quick reminder, just throwing it out there. Some of you really loved the chapters 1 through 3 or chapters 1 through 4 that were online there for a while, that PDF. Remember, the whole PDF of the entire book is way too massive for you to be able to pull up on any device, just online or even offline. You need to download it to your hard drive in order to be able to see it, just because it's too big. And as you can tell, I have it on my computer, which granted, we all know my computer has issues. It is what it is. Yeah. But at the same time, if you do want the full PDF version, that is a little buggy, but it's somewhat helpful. You can just email me, and then you guys can download it. So I'm going to close this PDF version, and let's see, we're in section 64. Number 71 is Okay, it is an application problem. The nice thing is it's not a... Oh, there's that Olympic guy in the pulling and the boxy thing. Anyway, number 71 is an application, but the nice thing is it's still not super mammoth in the sense of a word problem with a huge old scenario that's being fleshed out in lots of different ways. They're just saying, okay, it's work. We're moving from P to Q. Even though I said the test is going to be something on a horizontal plane, if you guys actually map this one out, he's not going to be as nice and neat in the sense of just moving horizontally. Now I can go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. I can see vector Q just by drawing initial point to terminal point. So that's my, ooh, it's moving from P to Q. Okay, that's the distance. If I found that horizontal, sorry, not the horizontal, that diagonal distance, that's the distance. So this thing isn't moving horizontally like everything else we've done. This is like one of those early projection problems where it's actually like moving up a hill or it's moving somehow along a surface diagonally. And then the force that's being exerted on it has 1, 4, 1, 2, 3. My D's in there. Well, I can still draw it. Okay, so long story short, I basically have this to this, and then I have a force being exerted that's kind of like this. And they're saying, okay, figure out the work done. The nice thing is the formula is the same in the sense of the background formula of force times distance. That's the same. The problem is I actually need the distance, which is the magnitude of vector PQ, because magnitude, remember, is the how muchness, it's the length, it's the greatness. It will actually solve for me how far this thing has moved if it went from P to Q. But then here's the bummer, is that I don't necessarily have an angle. Now, Spencer, I could technically do that whole angle between formula. I could get the angle. And then I could go ahead and take my magnitude of vector V, and I could actually do that, let's see, magnitude vector V times cosine of, I could do that formula, which is kind of like the one I showed a second ago with the right triangle. But the nice thing is I don't even need to work that hard, because what I could also do instead is just the dot product between vector PQ, which is distance, and vector V. What I'm trying to help you avoid in those ones where you're just dragging along a horizontal line, like the ground or something that's horizontal, is avoiding needing to get components. But the nice thing in this one is I can get the components really easily. So what's honestly easier than even thinking of, like, what's the cosine of the theta and getting the angle between and then figuring out the distances of each of these with magnitude formulas? Man, it'd be so much easier just to be like, oh, wait, it's the dot product? The dot product. So I could go ahead and just be like, hey, my work, multiplying my force times my distance, if I have components, it's just the dot product. And I think we did an example like that Thursday. But 4 times 1 would just be 4 plus 28. Double check me. I believe it should be 32. So if you have components, dot product is the way to go. But as far as word problems, it's not going to be traveling up, so you're going to have to like make your own components to do the dot product, or just say, forget it, it's a right triangle, I get it, it's force cosine of the angle times distance. Is that cool? All right, last call. I said I would do it. Nathan.
55.
55.
You know how to put that in the component.
And the nice thing is, Nathan, actually that was really well timed, not that you meant it to be that. But since I was just saying, like, hey, the dot product, if you have the components, it's awesome, it's easy. But I also mentioned, like, how sometimes it can be hard. This one isn't a word problem, so it's not necessarily proving my point, but it's just kind of capitalizing the fact that components can sometimes be messy to find. The nice thing is that this one, though, this is kind of like that number, was it number 12? I asked you guys if you had done components. It probably would have been a lot more helpful to do this orthogonal clue, which hopefully from your notes you guys remember 2 vectors are orthogonal if their dot product is 0. That's what I'm looking for. Components would be so much easier, and these linear combinations get messy. So I'm just, it's a scalar, Nathan. I can just distribute that. from vector operations, this would be a -1. So that'd be -1/4. And then this is just my 5 and 6. And then we can do the dot product. Which, I mean, looking at quickly, that's not super nice. I don't think this is going to work out so well because that's 15/4. My ones who don't like fractions, just throw them over 1. You're fine. Multiply across. And then I have -6/4. No. You don't even have to finish. You can just be like, it's not 0. Therefore, not orthogonal. Is that good? Another last call. Anything else? Sweet. Let's go to section 5. Alright, let me get rid of my webcam to try to speed up my computer. Let's get rid of my flash drive that keeps on wanting to come up. And let's talk about something that will seem so random in so many ways until you realize a lot of the math is the same as the vector formulas that we've been using. A lot of the math is the same as the vector formulas that we've been using. On this page, what looks familiar? Magnitude. Square root of a squared plus b squared. Looks familiar, yeah? What else looks familiar? I. But we haven't seen it in a while, right? But it does, because we've totally dealt with complex numbers that look like that, and we've totally dealt with magnitude formulas that look like this. But this, isn't this section 6.3? And wasn't this in, like, chapter 2? How on earth are they related? Well, we didn't really talk about way back when we talked about complex numbers, the fact that you can actually graph them. Oh, okay, we did. We talked about how you can't see them on a real graph. So if a quadratic has imaginary zeros, aka discriminants, quadratic formulas where you have negatives under the square roots, you won't see them on a graph. It's going to be a weird parabola that doesn't actually hit the axis, has no real zeros. So we did talk about on a real, like, XY axis, but there is a way of kind of graphing and showing complex numbers by basically redefining our XY axis. Redefining it so that the X's are the reals and the imaginaries are the Y's. And so when we look at this, I don't want you to write it in components. Please don't. It's not proper in any way, shape, or form. I'm going to erase it in like 2 seconds. But you can think about it kind of like you did with vectors. I'm going to erase it because that's super improper. You're not really allowed to do that or think that or show that. You can think that. But that's kind of what we're going to do because I'm going to go +3 because it's the real part, +3, and I'm going to go -2. So I can do my 3, which is my real, and my -2, it's on the I-axis. And I can show my complex numbers similar to how I would show a vector. Now, no arrow, because I'm not like pointing in that direction. I'm not exerting a force in that direction. It's literally kind of separate from vectors in that I'm not really doing physics right now. I'm going back to these complex numbers and saying, wait a minute, there's some sort of relationship with all this vector stuff. And another way of looking at complex numbers. So we have the old school from chapter 2, but now we have there's a graph to 3 minus 2, huh? But then also, this magnitude from vectors, so I'm going to go ahead and erase this and say, okay, it's okay for us to think magnitude, because magnitude is how much there is to it, which technically is what absolute value of numbers is doing as well. You can call it the magnitude. It's not the magnitude of the vector, but it is the magnitude of the number. But how we talk about magnitudes of numbers, even complex ones, is to use the absolute value. It's technically just going right in line with what we know of absolute value from normal numbers, like -20 or 17 or -5/2. How would you take the absolute value? The distance from it to the 0 on a number line. For a complex number, we can't use the same definition because we're not on a number line. We're not on a horizontal. We're on a 2-dimensional plane where, how much? Well, I have to figure out the distance that the complex number has, which is the exact same math as vectors because it's still a right triangle. Nathan?
Is the y-axis and x-axis always going to be imaginary?
Yes.
Or is it a normal switch?
No, we don't have to worry about bearings or anything like that. We're not going to do motor. He's probably thinking of your guys' last word problem in section 6.3 where the bearings made it so that everything got turned on end. Real is horizontal, imaginary is vertical. Yeah. So with this one, if we were to plot, I know when I say quadrant, some of you are like, unit circle. There's trig. I mean, it's in the title. But if I was to ask you to plot this one, can we realize that it would be in the fourth quadrant? The location of it. If I go 5 to the right and 12 down, because 5 is horizontal, positive means to the right. 12 is vertical, and negative means down. I'm in the fourth quadrant. If I wanted to find its I plotted it. Good, check. That one's done. Absolute value, that's the formula right above. You can think magnitude, it's perfect. It's basically the same idea. You can think 5, negative 12 if it helps you as far as like relating it to vectors. But long story short, we're just taking the horizontal leg and the vertical leg, and we're getting 169, which hopefully by now this year we know is 13. But what else we're going to see in this section is that, okay, there's the old school way of writing a complex number. There's the graph of now of a complex number. There's this whole like, hey, we can even take the absolute value of the complex number. It's just a little different because there's this whole two-dimensional aspect because we have real and imaginary all in one. It's like 2 dimensions kind of. But there's another form besides this one. There's another form. And the other form is like, well, wait a minute. If you could talk about this guy in terms of like over and down, can't you also talk about him in terms of rotation and out? It's like vectors. We can talk about vectors with overs and ups. We can also talk about vectors with directions and magnitudes. So the idea in this is like, okay, so we could talk about complex numbers just with the over and up, just with the real and the imaginary coefficients, but you can also talk about it in terms of trig. And that's where it ties in with vectors. Because this one, you guys took this page too, right? This one, let's zoom in a little bit, says, okay, cool, well, if what we were doing that whole time graphically was going over and up, as we talked about with vectors, it can be helpful to also think in terms of magnitude and direction. We're just going to label it a little bit differently. I mean, theta is still theta because it's an angle. No big deal. So we can think about it in terms of direction. That helps you tie it together with vectors. R, technically, though, it is kind of magnitude. We can still think of it in terms of magnitude, but why is it called R? Think unit circle, radius. That's kind of why it's called R. We're not using double lines because these aren't vectors, just the math and the formulas are so similar. But we can think magnitude, or another way of thinking of it, we can think the absolute value of a plus bi, which means that formula on the page before, square root of a squared plus b squared. My a is my horizontal component, but remember in this context that's real, the real coefficient, and then I have my vertical component, which in this case is my imaginary coefficient. But as far as formulas, I mean that's just labeling what everything is. As far as formulas, well, okay, if we need R, we can always use that square root of a squared plus b squared, because that's who he is. He's that diagonal length, aka magnitude. If we need theta, we can use exactly what we did with vectors, in that we can use tangent inverse. I'm not saying equals, and hopefully some of you remember why. But we can use tangent inverse to get to the right place. If we need A, let's say they give us trig form, because we could be going forwards to trig form or backwards to standard form. They could give us now complex numbers in either form, showing directions and magnitudes, or showing A's and B's. Wow, you're mad. Can you stop? Not you. It. Which is technically it. We can use A equals R cosine theta, and B equals R sine theta. Oh my goodness! It's like the one that I made you say like 5 times that one day, because no one knew how to find components. Magnitude cosine angle, magnitude sine angle. It's uncanny, the similarities. So if you came down here and you needed to actually like transform from one to the other, you could actually be like, wait a minute, I can get that whole r cosine of theta plus I sine of theta just by coming over here and saying, wait, isn't r just 1 squared plus negative root 3 squared? Which is the same thing as the square root of 4, which is just 2. I could throw that in the r spot. And couldn't I use that theta is equal to negative root 3 over 1? Wait a minute, square root of 3 over 3, 1 square root of 3. Isn't that the same thing as, if you threw it in your calculator, a negative 60-degree angle, aka negative pi over 3? Which we've been using degrees all chapter, and yet, ooh, some of you, because you're going to work on homework, and I'm so proud of you for doing that, radians comes back, because we're not really in vectors anymore. So we could have degrees, we could also have radians. You guys packed up at 2 minutes. But we could go ahead and throw this in. They're probably not going to use a negative, though. They're probably going to use the positive. And we can go the trig form. And the crazy thing is, guys, this one, all you have to do is multiply the two together. And then you could go ahead and pause. I commented on you guys packing up early for at least like 5 seconds. We can actually multiply this to get negative 5 root 2 over 2 plus 5 root 2 over 2, because I'm awesome and I know the unit circles. Do you? Bye. See you later.